We will be taking a look into the finite element method in a fluids application. Here we have the integral form of Stokes' flow. This will be discretized into a finite element formulation. To do so, we will first have to take a look into the finite element method. We will be using 4 node quadrilateral elements. These elements can be randomly shaped and sized. To make the calculations easier, each one is converted into local coordinates r and s, where the element is a square. All elements are defined within our domain only at the nodes. We then use an interpolation function or shape function to define the variable at any location within the element. U, for example, can be defined at any location within the element as shown here. In this case, we will use the simple set of shape functions. Note that each shape function has a value of 1 at its own node and a value of 0 at every other node. We will now substitute in the interpolated formulation to define the integral form as an interpolation from each node. This will allow us eventually to perform the integration without knowing anything about the velocity or pressure. Green Gauss will be applied to the viscous terms, which we will have to treat as a black box since there is not time to explain. This results in 2 terms, the first of which will cancel on any element boundary. From that, we can substitute in our interpolation of U. Since U is a vector of 4 scalars, it can be pulled outside of the integration. This is now in a form where we can integrate. We can now put this in the form shown at the top, which will allow us to directly solve for the pressure and velocity, where each of the stiffness submatrices is defined as such below for each element. The integration must be performed on each element and applied to the global system. You may have noticed that these equations are in terms of x and y. They need to be converted to the local coordinates r and s for the integration. To do so is simply a geometry problem. The Jacobian gives us the relation between the local and global coordinate systems that we need. However, the inverse is needed to define dn dx and dn dy with respect in terms of r and sl. These values are then substituted into the discretized equations. Now that we have things in terms of the local coordinate system, we can integrate. Gaussian quadrature is used since it is low cost and provides an exact solution for these integrations. The integration of the stiffness terms for an element is shown here. This integration is performed for each element. The element stiffness matrices are then transformed to the global node locations and assembled into 4 stiffness submatrices that are then further assembled into 1 stiffness matrix, while the degrees of freedom, u, v, and p, are assembled into a single vector. Boundary conditions are then applied. We will have a no slip at the hole in the center and an inflow on the left boundary. All other boundaries will have a no forcing condition. This puts us in a situation where we have some known forces and some known degrees of freedom, which will make the solution a bit tricky. Since we know certain degrees of freedom and how those degrees of freedom affect the forcing, we can calculate their contribution to the load. This will then be added into the forcing for each affected node. The system with known degrees of freedom are then dropped, leaving us with a reduced stiffness matrix, all unknown degrees of freedom in their forcing, including the effects of the known degrees of freedom. The unknown degrees of freedom can now be directly solved for. In my formulation, however, the stiffness matrix is nearly singular, either due to bad formulation or a mistake that I was unable to find, the result of which is an incorrect solution. The solution can now be plotted. The plotting must be done element by element. A patch function is useful. It allows plotting of each element in space and provides interpolation of the solution between each node. Unfortunately, since the system was not properly solved, we will have to use this incorrect solution as an example.
Created using Powtoon.